Hello. In the last lecture, we have defined differential function on a regular surface. The purpose of this lecture to give some examples of differential function on a surface. Okay, so then let us begin. So let me first recall the definition of a differentiable function. So let us take S to be a regular surface in R3. So a function f from S to Rm, okay, is said to be differentiable if for all p belonging to S, so there exists a surface patch u comma sigma such that p is contained in sigma u and the composition f compose sigma, okay, so is a differentiable map on U. Okay. Okay. So this U, it is an open subset of R2. So if I draw a picture, so this is my say surface. So suppose this is my surface, and let us take point P. So for each point, I have a surface patch like this. So this is my U, and I have a map sigma defined on this U, and sigma of U is this set. Okay, and now F, it is a map defined on the surface S. Okay, so therefore this F compose sigma, it makes sense. So F compose sigma, if it is differentiable, so then we say this F to be differentiable. Okay, all right. So in the last class also we have seen that this definition is well defined in the sense that, so if I change the surface patch, okay, suppose psi b comma psi is another surface patch such that p belongs to psi b, okay, so then f compose psi is again, it is differentiable. So this definition is well defined. So now let me give some examples. So height function. So what do you mean by height function? So let us take a let us take any regular surface in R3. So let S be a regular surface in R3 and B be any unit vector in R3. Okay. So the height function HB so this is a real valued function on S. So height function HB relative to B. So this height function, it depends on this unit vector B is given by HB. P is equal to the dot product of P with P. So P, it belongs to S. Okay. So for instance, so if I take, so suppose B is this unit normal vector and the surface is like this. So this is my unit normal vector. And now if I take any point P on the surface S, so you take this line segment joining this origin to P, and this P dot B, it so gives you the orthogonal projection on this z-axis. So you'll get this P dot B here. Okay, so this is the meaning of height function. Okay, so let us now give another differentiable function. Okay, so why this is a differentiable function? So f is a differentiable function on S. Okay, so so you can define this capital HB to be the following. So HB XY Z is equal to the dot product of XYZ with B. Suppose B is B1, B2, B3. So, and X, Y, Z, it is varying in R3. So this is basically this thing, X B1 plus Y B2 plus Z B3. Okay, so this function, so HB it is a function from R3 to R. So HB is differentiable on R3. Okay, and so this HP, small hb, is equal to capital HB restricted to S. Okay, so because of that, so this function, this height function, is differentiable. So it is a restriction function of a differentiable function. So that's why it is differentiable. Okay. So next example, let us take square distance. So square distance of S from a fixed point in R3. So square, let me call it square distance function. Okay, so how do you define this function? So let us take a point P naught belongs to R3. Okay, and so this distance function, so f of P is equal to norm of P minus P naught square, where the speed belongs to S. Okay, so again you can take this P, it is in R3, so then it will be a differential function, and if you restrict to S, so you'll get this small f, so therefore this f is a differentiable function on S. Okay, we have defined differential function from S to Rm. So now how to define a differential function between two surfaces? Differential function between surfaces. Okay, so let us take two surfaces. So let S1 and S2 be two regular surfaces in R3. And let us take B1 to be an open subset of S1. So let B1 be an open subset of S1. And F B1 to S2 be a continuous map. Okay, so we say F is differentiable at P belongs to B1 if so there exist surface patches U1 phi 1, U2 phi 2 of S1 S2 respectively, such that the following holds. Okay, so what are my conditions? So this P, it has to belong to this phi 1 U1, and also I demand that this phi 1 U1 is contained in B1. So this is one thing. Second is because this map f is continuous, so what I can take, so f of phi 1 u1 is contained in phi 2 u2. Okay, and the third thing is, so now if I take this composition, phi 2 inverse compose f compose phi 1, so it is a map from u1 to u2. So this is a differentiable map. Okay, so note that here this u1 it is contained in R2, u2 also it is contained in R2. Okay, so I have this this following diagram. So this is my u1, this phi 1, it takes u1 to this open set phi 1 u1 in the surface. So suppose this is my surface S1, and this is my, say, B1. The function f is defined on this B1. Okay, the image of f8 lands inside the surface S2. Yeah, so this is the, you can say this the, so this f of B1, and so inside this, so what you have, this phi 2 of u2, maybe I can draw like this. So this is phi 2 u2, and again inside this what you have, so this is f of phi 1 of u1. Yeah, so this f, now it is here, okay, inside this green open set. All right, so this is my u2, which is sitting inside this R2, and now I have a map from u2 to this thing. Okay, so therefore, so this, so composition, so this composition, if I go like this, so first this phi 1 and then f, and then you take f2 phi 2 inverse. Okay, so this composition, it makes sense. If it is a differential map, so then we call this f to be differentiable at P. So f is differentiable at, f is differentiable on B1 if f is differentiable at each point of of by. Okay, so now let me quickly give you an example of a differentiable function from one surface to another surface. So let us take this function. So let fxyz is equal to ax a by cz. Okay, so this function, it is from R3 to R3. So f is a differentiable function. Okay, and now if I restrict this function to unit sphere, so let S2 equal to this unit sphere. So what will be f of S2? So f of S2 is this ellipsoid that you can check. Okay. So let us denote E2 to be this ellipsoid. Okay. So f restricted to S2, it is a map from this unit sphere to this ellipsoid. So this is a differentiable map. So this is one example. So another example. So let us take this infinite cylinder. So S1 cross R, so which is nothing but uh, cos t sin t s. So t, it varies in R, s also it varies in R. Okay, so if I take this thing and now define, so f of cos t comma sin t comma s. So this to be the following. It is cos of uh, so just wait. If you take cos of t plus 2 pi s comma t sine of t plus 2 pi s comma s. Okay, so this f is, again, it is a differentiable map. So f is a differentiable map. So what is this map doing is the following. So if I take the cylinder, so this map, it takes cylinder to cylinder. And suppose if I take, suppose this is my xy plane, and let us take s equals to 0. So if I take s equals to 0, so what we'll get? So I'll get cos t comma sin t here. Suppose this point is my cos t comma sin t comma 0. Okay. And now if I apply f on this thing, so f of cos t comma sin t comma 0, so by the definition of this map, it will be equal to again the same point. So f will fix this point. So again you'll get the same point here, the same point here. Okay. And now if I take s equal to 1, so what we'll get? So if I take s equal to 1, so f of cos t comma sin t comma 1, so this is equal to cos of t plus 2 pi sine of t plus 2 pi comma 1. Again it is equal to cos t comma sin t comma 1. So again we are getting the same point. So this point is cos t comma sin t comma 1. So this point is again fixed. Okay. So what this map is doing, so if I take this vertical line here, so this is making it twist. So this map is twisting. So f of this blue line, it will be like this. Okay. So this map f is called, so f is called dent twist. Okay. So this dent twist, it is a differential map. Okay. So I'll stop.